This is Himabindu, Assistant Professor in IARE College. So today we will like to explain about the concepts called definitions and terminologies on Turing machines. So how many definitions are there? We will discuss in this video about the Turing machine. So what is meant by Turing machine? So what it contains? So how we will generally denote this Turing machine? So generally this Turing machine consists of a tape of infinite length. So previously we discussed about the push-down automata and the context sensitive, that is nothing but linearly bound automata. In that one we have shown that one is a stack and infinite length of tape in the linearly bound automata. So here we are going to discuss about the infinite length of tape, what we are using in the Turing machine. So the Turing machine, which is consist of an infinite length of tape. So in this one, generally we will represent this tape as an infinite length. So here left hand side and right hand side, we have there is no end for this one. So infinite amount of memory is there in the infinite tape, and which write operations can be performed. So which we can write the operations on this tape. So generally we have the Turing machine, which consists of moves like the header is moving from one direction to another direction, that is left, right direction and left direction, that is a finite controller. So based on the transition, this finite control can move either left or right in the transition diagram. So this is about the Turing machine, which consists of an infinite length tape, and in that one infinite cells are there. Generally this, if you filled this tape with the input symbols, whatever left is there, so that left part we can fill it with the blank symbol. So only the input value we are going to place in the tape, then the remaining all part will be as a blank symbol. So this is about the Turing machine, and define the recursive enumerable languages. So here how we will design this Turing machine means for what languages, what type of languages we are going to use this Turing machine, in the sense recursive enumerable languages. So what is meant by recursive enumerable languages? So the language which can be accepted or recognized by the Turing machine, which means it will enter into final state. So after reading the input string, when it is reaching the final state, for the string of languages, so the language which have suppose here it is a language, so which type of strings according to this language is there, that will be accepted by the Turing machine, and may or may not enter into the result state. So here whenever the string which belongs to that language, it will enter into the final state, or it may or may not reject state is there in the for the all the strings, so which are not a part of the language. So the strings which are not part of a language, that is for that languages, it will enter into a final state, or it will not enter into a reject state or reject state. There is no strict rule for this one, recursive enumerable languages. And coming to the recursive languages, so recursive, this generally will represent with the RE, and this is RC. So RCE, recursive enumerable languages. So here the recursive languages, which is a subpart of recursive enumerable languages, that is nothing but RE. RCE is a subset of recursive enumerable languages. So here it can same definition, but which means the rejecting state for the which are not part of a language. So here is the two things we need to observe: recursive enumerable and recursive languages. So recursive languages are strictly rejecting, it is entering to the strictly rejecting state when the string is not belong to that language. So this is the two things we need to observe for the recursive enumerable languages and recursive languages. And what is meant by Church's hypothesis? Church hypothesis is also formally commonly known as Church's thesis. So, Church thesis, and says that any real world computation can be translated into a equivalent computation. So here, whatever there like addition, multiplication, whatever the real computation is there, that will be given. That will be automatically. We will equivalent computation will be performed by the Turing machine. So that is the thing. But this statement says that Church's hypothesis. And describe the counter mission. So what is meant by counter mission? So counter mission is a consist of read only. So if we have two tapes, suppose here we have a two tapes. One is here the input it is having, it is infinite length, infinite tape we are taking. So this two tapes in this one, first one is a read only tape. And this one is read and write operation can be performed. Read and write operations can be performed. So here in the read only operator, we can also say that this is the offline Turing machine. And read only tape which have the values. While reading, we just in this tape we just read operation is performed, and in this tape after reading this input symbol we can write the replacement value like this. And this is about the counter mission. So it consists of read only input tape, infinite controller, fixed number of counters, each capable of storing arbitrary natural numbers. Define linearly bound automata. So coming to the Chomsky hierarchy, this one find linearly bound automata which is formed with the languages, context sensitive languages. So here the linearly bound automata restricted type. So the same thing, same construction, same model as a Turing machine, but there is a restriction, that is a restricted type of Turing machine. So generally in the Turing machine, we will take the infinite length, but in the linearly bound automata, we are not taking the infinite. Instead of this infinite, we are taking the bounded tape. So that is we are limiting the memory here. So that's why we can call it as a restricted type of Turing machine. So here, and which generates the context sensitive languages. So which generate, so what type of grammars will generate these languages? So here type 1 grammars, that is the context sensitive grammars which can generate the context sensitive languages. And the list Chomsky hierarchy of languages. So here, we have the Chomsky hierarchy. This one will directly say that. So first one is a regular language, and second one is the context free language, and third one is the context sensitive language, and fourth one is recursive enumerable languages. So these are all the 4 types of languages we have in the Chomsky hierarchy of the languages. And define the regular grammars. So here we are going to define about the grammars. So here how many types of grammars in Chomsky hierarchy? So type 0, so type 3, and type 2, and type 1, and type 0. So these are the 4 types of grammars we have in the Chomsky hierarchy. In this one, this type 3 is a regular grammars, and type 0 is a context free grammars, and type 1 is a context sensitive grammars, and type 0 is a unrestricted grammar. So these are the 4 types of grammars we have in the Chomsky hierarchy. In this one, first one is about the type 3 grammar. So what it generates? So it generates the grammar. So this is named as a type 3 grammar, and it generates the grammar like a single non-terminal value. That is left hand side. It is having the V tends to. It is called right hand side. So right hand side consists of a single terminal or. So single terminal or. single terminal followed by the non-terminal, like V tends to A, capital E. So these are the only, this is the regular grammars. So, and this is the production rules for the regular grammars. And coming to the type 2 grammar, that is nothing but it is a context free grammar. So context free grammars which are generated by the generate the language, context free languages will be generated, and the productions must be in the form of A tends to alpha or lambda. So here A tends to alpha. So here A side, so left hand side it is a single non-terminal. So and which left hand side it is a combination of terminal and non-terminal. So that is A, capital A or E. So like this we have the restriction in the type 2 grammar, that is a context free grammar. So in the left hand side we have a single non-terminal value. And describe the context free grammars, that is nothing but, so both are same, the context free grammars or type 2 grammars are same. And context sensitive grammar, so context sensitive grammar is a type 1 grammar, so which generates the context sensitive languages. Context sensitive languages, the productions must be in the form of alpha tends to beta. So here alpha and beta, so there is a restriction like in the production rule, left hand side, so left hand side is greater than or equal to right hand side length. So here beta is the value, so beta is nothing but the value, sorry, here beta is right hand side, this is RHS and this is left hand side. So left, every time left hand right hand side should be length, the length of the right hand side should be more when compared with the left hand side. So example, so here A, yes, I'll take A, S, A. So this is acceptable, but A, S, A tends to A, S, it is not acceptable. Why? Because the length of the right hand side, it is less when compared to the left hand side. So this is not acceptable. This is the context sensitive grammar. And unrestricted grammar, that is nothing but a type 0 grammar. So type 0 grammar. So this type 0 grammars we can also generate the recursive enumerable languages. The productions, there is a no restriction. So the left hand side and right hand side, where there is a no restriction in the length is no restricted. So the length of the grammar, the length of the production, which is not a restriction in this Turing machine. And define push-down automata. So we have we have the Chomsky hierarchy. So in this one, first we will take the regular grammars, and with that regular grammars we can generate the regular languages, and with the regular languages we can generate we can generate the finite automata. And push-down automata is the subset of finite automata, and linearly bound automata is a subset of pushdown and PDA and PFA and Turing machine. So these are the hierarchy which we are following in the formal languages. So here in this one, first one is a finite automata, and for second one is a pushdown automata. What is meant by pushdown automata? Generally we will represent the pushdown automata FSM plus stack. So here in FSM, that is nothing but FA, it is having some limitation, like it is not having the infinite memory to count or remember the number of strings what we are having in the language. It can't remember. So that's why we are going to push down automata. So the push down automata which includes the stack. So this stacks will perform like push and pop operation. With that operation, we can remember the value of the strings, input symbols in the strings. So that's why we are PDA is more powerful than FE. And multi-tape Turing machine. So multi-tape Turing machine. So generally the standard Turing machine which we have a single infinite tape. But coming to the multi-tape Turing machine, so multiple tapes we are going to take. In this one, this multiple tapes where each tape is accessed by the separate header. So each tape is accessed by the separate header. So here we have taken the simple two tapes. So two tapes are individually operated by the two headers, that is FC finite controller and finite controller, and each head can move independently on other heads. So initially the input is on tape 1 and others on the blank. So here initially this is on this tape header is on one input, and this one initially it is a blank. So like that, multi-tape Turing machine is going to be designed. And Chomsky hierarchy of languages. How many types of languages we have? So here we already discussed the grammars, so type 0, type 3 and type 2 and type 1 and type 0. So these are the Chomsky hierarchy of the grammars. And how Turing machine with the two-dimensional tapes. So two-dimensional tapes in the sense, so two-dimensional, so this is left-hand side and right-hand side, it can move. So here a two-dimensional tape, one finite control, one write the head and one two-dimensional tape. So here the tape has a top end and left end, but extends indefinitely to the right and down. So two-dimensional in the sense it can move in the two directions, like so generally we saw that left direction and right direction, but in the two-dimensional it can move in a top and down. So the four operations going to be performed on the two-dimensional tapes. And Turing machine with the infinite tape. So a tape has an infinite length and divided into cells. So infinite length. So this is the infinite length. Whenever the input is there, we will fill with the input, and remaining all are blank symbols. And deterministic Turing machine. So determinism in the sense, in first unit onwards we are discussing there is a no choice. So single choice is there for the determinism. So single choices. It is believed that everything can be computed can be by the Turing machine. So that means, so here whatever the computation is there, that computation for the input value. So if you observe the value of infinite tape. So here when we are reading this A, we need to replace with X. So this reading of A here in this header point, so this replacement of X is possible in the one tape only. So it cannot be possible in the multiple tapes. So that means the multiple states are there. So determinism, they generally will represent the Q naught, which is equivalent to, will take one input and going to the another state. It is not going to with the same input, it is not going to the next state. So this is not happened in the determinism. So same thing, the concept is going to be happened in the deterministic Turing machine. And multi-track Turing machine. So multi-track, so multiple tape, a specific type of multi-tape Turing machine which contains multiple tracks. So here multiple tracks, just one tape head reads. So here only one tape, so FC is there, and write on all the tracks. So that means, so multiple tracks. So this header will replace the values like this, and here single tape header reads the symbols from the stack on the tape step. So it accepts the recursive enumerable languages like normal single track. So these are this multi-track Turing machine, which is equivalent to the normal standard Turing machine. Describe type 0 grammar. So type 0 grammar generates recursive enumerable languages. So here in the Chomsky hierarchy, this is the highest grammar. So that's why we named as a type 0 grammar. And type 1 grammar is a context sensitive grammar. So that means we can generate or we can construct the model linearly bound automata. And the language what we are going to which generates the type 1 grammar is context sensitive languages. And recall the type 2 grammar. So here the recalling type 2 grammar which we have, type 2 grammar is a context sensitive grammar which we have the values like left hand side and right hand side. It is a condition. So the right hand side should be the length of the right hand side production rule is more when compared with the left hand side. And type 0 type 3 grammars. So the type 3 grammars generate regular languages. So like regular languages which we have the restrictions like we don't it should be like left hand side a single value should be there, that is nothing but non-terminal value, and right hand side it should be a combination of either terminal or non-terminal, or else a single terminal is also accepted. So only two, length is two only. So these two only accepted. Other than this grammar or production rule, it is not going to be accepted by the regular grammar. And briefly write about the author of the Turing mission. So Turing mission author is Alan Turing, was an English mathematician, a computer scientist and logician and cryptanalyst and philosopher and theoretical. So born in 23 June 1912 and here died in 7th June 1954. So here is about the author and what are the awards got for the Alan Turing. So it is award name is a UK award, that is a United Kingdom award, Smith's Prize Education. So education is a Princeton University. So here is the details about the Alan Turing. So this Turing mission was constructed, designed by the author Alan Turing. That's why the name Alan Turing name it is the Turing mission name with the author name. So this is all about the fifth unit, Turing mission definition and terminology. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.